He's not here. Well, he was.
Yes, sir. We are live now, sir. Yes.
Okay, so you can start.
Okay, so we're on live now. So it's my pleasure to. What? We're live now. Yeah, so it's my pleasure to. Now I hear myself. My pleasure to introduce Didier Buchs, who is a professor at the University of Geneva, who works on formal methods and applied to the modeling and verification of cyber physical systems. He has a very long experience in Petrinets, and he's going to talk about modeling and verification of cyber physical systems. So go ahead, Didier.
Okay, thank you, Dominique, for the introduction. So it's Geneva in English. It's not Genova, which is in Italy. Okay, so from Geneva. Okay, so no problem. Okay, so I will talk about modeling and verifying cyber physical systems. So maybe the part concerning really physical system will be limited in my talk. I will more concentrate on modeling and verification of complex system, I would say. So the main starting point is just to examine a little bit the process of development of cyber physical systems. So there is an informal part, which is to analyze the system, and there is a formal part where you have different activities concerning the modeling of the control, the cyber part, and modeling of the physical systems. So the idea is at the end to produce only one artifact, but I will discuss mainly the line where there is a modeling of control. We have to establish probably some modularity in the model in order to decompose, to have an approach decomposing the problem into modular submodels. So this is another aspect. And finally, taking both information, we will be able to simulate the systems. And the idea around what we are doing is to be able to produce something that can integrate the physical and the cyber part in order to be able to do simulation. This is a part that has been already described yesterday by Hans van Geluwe. So I don't want to discuss too much about the functional mockup units, which is the part where we describe how to simulate the system. So my concern is more about modeling and verification. So this is the part that are formal. So here, the formal part of the activity. And I would like to propose some approach, and in particular, to show that using a high-level model, we can really model in detail the system and later perform verification. So it means that I need to model the system using a high-level model, and I added the fact that it's a concurrent model. It means that in most of the system, we have to take care of the possible concurrency of different activities. So we need to be able to model such aspect of the system. Then it's necessary to decompose the system in order to be able to check every part of the system. Otherwise, the system is usually too complex. So there is a modularity aspect, which is also necessary in the system. And finally, the verification of the components. So in the term verification, I think there is a presenter that before introduced the terminology, don't remember his name, but the idea is that there is different possible approach to verify a system. There is the proof techniques, in general supported by proof assistants. In this case, we don't need to analyze the behavior of the system directly. You are using, in fact, logical systems for which we can develop proofs by using various techniques such as induction, co-induction, and so on. So this is a domain where we need human intervention because we need to write the proofs and maybe the proof assistant will check them for you. Model checking is a technique which is more press button, in which you want to provide a model and later, using appropriate technique, check if a formula is verified or not. So this approach needs a lot of hypotheses because you need, in general, to reduce the behaviors to something finite. Otherwise, you are not able to do automatically this model checking task. And finally, there is a testing approach, which is a way of checking the system for a limited number of cases. And so there is an hypothesis directly, which is the fact that this limited testing will be able to discover errors. So the main idea of testing is, in general, to discover errors. Okay, so for the rest of the talk, I will concentrate on model checking. It means using techniques for automatically proof property of system under some assumption about the system, which is in general the finiteness of the state space. So for the language that I will use for the verification, I will show you the fact that temporal logic is an approach for describing the expected properties, and using symbolic model checking, we can perform those checking. So I would like first to describe a little bit what it is necessary to do for modeling. In fact, I think it was already discussed yesterday concerning the use of PetriNet. It's necessary to understand that PetriNet is a class of formalism. In fact, there is a basic model which was invented by Carl Adam Petri, but from this initial model, many extensions have been proposed. There is extension concerning the behavior. So it means to take into account additional information, for instance, the time. There is many approaches concerning the time, and there is also approaches concerning the expressivity. Probably you if you know a little bit about PetriNet, you heard about the fact that there is, for instance, inhibitor arcs that increase the expressiveness of PetriNet, which is not identical to the Turing machine, for instance. So this is a computational expressivity. If you look at the structural aspect, it's also important to understand that there is many approaches that have been defined over PetriNet in order to structure the PetriNet. In terms of place and transition, but also to modularize the PetriNet, so to produce modules that have different mechanisms for communicating, for being composed in the final model. So there is many dialects. I just mentioned a few ideas that have been introduced, but I don't want to do a summary of all possible PetriNet definition. What it is important to mention is the fact that all PetriNets have in common the fact that the state is distributed over substate, which is a notion of place. That transition represents possible discrete events. So this is important, the fact that it's discrete. And finally, that tokens represent the current state of the systems, and the arcs represent the pre and post condition. So there is the states, events, pre and post condition, which are really important in the PetriNet. So they are always present in all dialects. So I just would like to show you that from the basic PetriNet, we can really decompose a system into some subsystems. So all subsystems are PetriNets themselves. And there is a glue that, for instance, combine. So this is a glue that combine the different models in order to define the global behavior. So in general, this is the approach of the modularization. There is a way of defining some parts and combining the larger part. So I put some reference at the end of the presentation that can give you some pointer to additional information. Okay, so for the modeling, I don't want to do much more. I would like now to look a little bit about how to use the modularity in cyber physical systems. So the idea is to model the cyber parts, to encapsulate in functional mockup units. So this was already mentioned yesterday. And now the idea is each component can be checked and verified in isolation using model checking. And finally, the whole system has a behavior which depends on the semantic of the glue in terms of FMU or functional mockup unit or PetriNet functional mockup unit. This is called the master algorithms. So this is the glue between the various components of the systems. Okay, so now I would like to talk a little bit more about model checking, which is the main part of my talk. Okay, so what is model checking? Model checking is the fact that we want to verify some property on models. So the process of doing model checking is, in general, to build the semantics of a system, to define the properties that you want to check, for instance, using a temporal logic, and finally to verify the property. So this is the model. But when I'm talking about model, here is not the syntactic definition of the model, but it's the behavioral definition of the model. More or less, it's a semantic of a PetriNet. The phi is a formula to check in CTL, for instance, or LTL. So you have formulas, and you want to check that this formula is satisfied for the models. And this is done by the model checking techniques. So now the idea is, how can we do this efficiently? And what are the problems related to this activity? So in general, we need to define the model, which is itself a problem. We need to do the model checking, and so this could be done by specific algorithms. So we will define algorithms for doing the model checking, and for the construction of the semantics of the model, so the model itself, we can use, in fact, specific representation. And this is where this process has different possible instantiation. So I will discuss a little bit now what can we do for doing this process of verification. So this is not only, in fact, model checking, this is a general process of verification. Okay, so the question is, what are the barriers for using model checking? What is limiting is this aspect of verification. There is part which is not the purpose of what I will present, which is, for instance, the fact that the system is very complex. Okay. In this case, the solution would be, in general, to have a dedicated language. For instance, a DSL defined for the particular systems that we are studying. If you look at the literature, for instance, Promella is defined for concurrent processes. So this is a DSL, but you can imagine a more dedicated DSL for a specific domain. The other problem which appears very often in the engineering activity is the fact that formal languages are difficult to master because they are based on mathematics. Even if these mathematics are simple, they are often difficult to master, or they need a long training before being used. So one idea could be that based on the DSL, you avoid a little bit the complexity of this aspect. Otherwise, the main problem, in fact, in model checking for trained engineering is the problem of state space explosion. What is state space explosion? Probably everyone knows that it's really the fact that some problems have a combinatorial combination of possible execution that it's not possible to enumerate this combination. A simple example is can be given from the dynamic philosopher problem. If you look at the dynamic philosopher problem, this problem is really the fact that there is many philosophers around the table that want to go to the state eat or think. And for this, they need some protocol to acquire the forks and be able to pass from the think state to the eat state. So this is something which is a little bit heavy because the combinatorial implies a lot of combination. So for a problem which is easy to write, you have a number of states which is not manageable. For instance, one proof of this is just the fact that the number of atoms in the universe is largely smaller than the number of states of this in this case. So what can we do? In this case, there is only one solution, which is to not examine directly all states. So how to do this? There is more or less four kind of possible approaches. There is the first approach, which is the fact that it's possible to reduce the search space. So instead of looking at each state, we will look at, for instance, an execution which is significant and it's not necessary to look at some other executions. And so the idea is to have representative of the interesting execution, for instance. There is another approach which is called abstraction, where the idea is to reduce simply the complexity of the system and by avoiding some details. And the issue here is that we need a way to be sure that what we are proving is correct with respect to the more detailed system. So there is a process called CIGAR that can be done for detailing this refinement process, starting from very abstract system to very concrete one. In general, all these approaches have good case where there is a possibility of reducing really significantly the state space, and there is pathological cases where you cannot do anything. So there is the remaining very difficult problem. Symmetry-based, this is another technique where you are using quotient graphs in order to check a system. It means that you are, in fact, identifying states that look very similar. One idea would be if you have several nodes in a system, maybe it's not necessary to consider all nodes, but just the fact that you are communicating between one node and another one without knowing exactly which one. So this is a possibility for reducing the complexity of the work. Even if you are doing exhaustive enumeration, it could be improved by very clever way of implementing things. It could be the time spent in computing the exhaustive set can be reduced. So this is a way also to improve the computation. So by using tricky way of storing the information and computing faster things. So this is something which has a big limitation in general. And lastly, there is the approach where you can simply consider only a subpart of the system because you can reduce computation or representation. So this is, for instance, the idea of symbolic approaches, where the idea is to be able to share some similar behavior within the system and in order to reduce the amount of work to do. And there is the last approach, which is more or less the similar way, because the idea is to reduce the satisfiability problem to a subpart of the whole formula. Okay, so now I have several slides that I will skip because otherwise it will be too long. So for instance, this is an aspect of the partial order that is used for looking only on a subpart of the possible behavior. So we are just using the path in bold instead of all paths. Abstraction is the CIGAR approach. So here there is the algorithms that is used for the CIGAR approach. The CIGAR approach is a way of refining the abstraction in order to be sure that we are not dealing with wrong negative answer. Otherwise, quotient graphs where we are quotienting the system, as in this example with two different computers that we don't identify directly. We are just identifying the class of different computers. So it's an approach which reduces the number of possible states. So for the symbolic approach, which is the approach that I will detail a little bit, the idea is to have a symbolic representation of the state. So the idea is mainly that we can represent the Cartesian product with a limited number of elements. So this is the idea of well-known BDD. The BDD is the original approach. I will show you that we can really extend this BDD approach to something much more powerful in order to be able to apply it for more complex systems. Because using BDD directly needs a lot of particular encoding of the state, which are not so easy to do. So I will first talk a little bit about the notion of encoding and the way it is done in symbolic approaches. So the main idea of decision diagram is to, instead of representing one state after one, each state, the idea is to represent sets of state. So the idea is, if I'm able to present a set of states, and ideally I am able to perform an operation that I will call an homomorphism, I'm able to transform this set globally into another set. This is very similar to the approach of SIMD, where there is only one program, so this is the homomorphism, that work on several informations. It's important to respect some properties, so this is why we need this idea of homomorphisms, because we don't want to have a different result if we consider separately subpart. For instance, the whole set is U, so the subsets are U1 and U2. So I would like to have the same result if I'm concerning separately U1, U2, or U itself. So this is a domain where there is plenty of approaches. So I mentioned here one article which generalizes this principle of decision diagrams. The idea is that finally a decision diagram is a graph of nodes, interrelated nodes, and for these nodes we have different operations and different way of representing the system. So okay, so as I promised, the first aspect I would like to discuss a little bit is what about the transformation? Because the idea is that I would like to present a set of states, but the idea is to transform this set into a representation that is really much more simple, and it's also much more simple to apply transformation on this operation on this subset to produce a new subset. So the idea is to show that this is a general principle that is already used in many mathematical tools. For instance, Fourier transform, Laplace transforms are similar, but the way they are representing is a little bit different. But the idea is really that it's really simpler to implement, for instance, a filter on spectral transformation than on the original signal. So this is the same for data decision diagram, where there is a set of states, and we want to transform the set of states into a representation which is easier to work on. So what is this representation? This is this is the issue, and also what are how can we what can we expect as a reduction of complexity with these approaches? So just an example, if we solve the n-queen problem, it's the problem where we have to place n-queen on a chessboard. If we take n as a number of line and column, we can show that, for instance, the set of states is very important. in terms of BDD, here it's a reduced order BDD, we can show that there is a real reduction of the number of states, because considering 4,000 states is really better than 2 power 64. So this is where the decision diagram can really improve the process of model checking, because you can really reduce the number of real states that you have to examine. So in order to do this, I will now show you, I hope I have time to do it. I will show you how to do this and how to generalize the idea of BDD. So I'm proposing first to examine the notion of set family decision diagram. Why set family? So it means that I will represent some sets and I would like to encode those sets on a structure. What is the structure? The structure is very similar to the BDD. It's an acyclic graph where there is for each node a term, and for the successor of nodes, there is two successors indicating if the term is included or not in the final representation. Okay, so probably it's better to have an example. So this is a set family decision diagram. So for those that know BDD, it's very similar. You will see just that the operation and the structure is a little bit different after reduction. Okay, but the idea is with this diagram to encode several sets, the set ABC, AD, BC, and D. If you look at BC, for instance, where is BC? It's BC, it's when A is not included. So this is this path, B, C, D. It's a path representing this set. So now, starting from this, you can see that it's relatively complex. But the interest of all this aspect is to be able to reduce this graph to something very really simplified, where all the information are kept, but you can represent them with less information. So here, I would like just to show you very quickly various possible of reducing this graph. For instance, you can reduce the terminal nodes. So the nodes that indicating if the set is in the set or not. So with the bottom and top. So this is where we are just collecting the final nodes to the same node. Then you can find some nodes that are not useful, because for instance, D here is never used because bottom means that there is no D inside. So this D is not useful, so you can remove them, all these. Then you can factorize. So factorization is an important aspect. So these two graphs are similar. So you can reduce to those graphs. So now we have just to add the fact that this graph is unique, which is relatively important. Well, it should be unique, but why it is unique? It is unique because we impose an order between the variables. So the choice of the order is important and will produce something unique. Here, in this case, there is a small issue, which is about the fact that we don't need some information here, which are the fact that here C indicates, for instance, here indicates that it's taken but not taken. So it means something which is not very useful, a little bit contradictory. So the idea is to remove those nodes. And finally, to have a similar representation. So this representation is unique due to the order and due to the fact that there is no a link between a node. So here we don't need a node to pointing to a take node pointing to the bottom. So here you have only nodes that point to another node, or nodes, take nodes that point to a take, or the other nodes, the not take node, which point to bottom. So in this case, you have exactly the sets that are mentioned here. So this unicity of the representation is very important, because it is now possible to do operation on subparts without thinking about the context in which they are defined. So if I want to represent the state of a Petri net, such as the Petri net that I mentioned here, so the state, the initial state of this Petri net can be simply represented by this diagram. Okay, but this diagram suffers from a big limitation, which is the fact that I cannot represent more than one token into a place. Okay, so this is why what set decision diagrams are relatively too simple. We need to extend them, but with the structure that we have, it's easy to extend them, because the idea is just to put on the arcs a number, and with this idea, we have the possibility to represent a function. And we can see here an example. With this example, I have two places. I have the possibility to say that P1 has 3 tokens and P2 has 5 tokens, which is defined by this part. But I can also collect the fact that P1 has only 1 token 2, and in fact, P2 has no token. Okay, so with this diagram, we are representing this set of states. Okay, if we want to extend, to add one additional state, which is this state here, the fact that you have also the state where P1 has a value 3 and P2 has a value 6, which is another state of the Petri net, for instance. What do you need to add to this model, to the decision diagram? We need just to add this link, because in this case, the prefix, which is the part here, the prefix of this state is similar to the prefix of that state. So in this case, we can share the prefix and then have 2 postfix, which are here. So this is a very efficient structure, and we are able to manage to represent a huge number of states. So in order to represent a state, it's relatively good. Now we have to discuss a little bit, because I don't have time to do much more. I would like to discuss a little bit the operations that we can apply. As I said before, the operations are homomorphic. It means that there should be similar if we consider subset or not of the systems. But what it is also important is how we can really apply such techniques in order to reduce the computation time. So the idea would be not to decompose when we are, for instance, looking at the state space of a Petri net. What we are usually do, we are, if I'm looking, this is the algorithm of state space computation for individual states. What we are doing, in general, we are choosing here a state, and from this state, we are trying to apply all transition to compute the resulting state. This is the techniques that it is used. So if it is variable, then we compute the next state. Okay, this is good if we cannot do better, but if we can apply for all existing state the computation of the successor transition, so it would be really much more efficient. This is the idea of the global state computation. So instead of taking one marking, we are taking several markings. And with this several marking, we are applying an homomorphism, which is this homomorphism producing a new set of states. And the idea would be to check the fixed point. So this is the fixed point. When we reach the fixed point, it means that we have no new state to examine. Why it is efficient? For several reasons. It is efficient because there is sharing, but it's also efficient because we have in the implementation a system of memorization. It means to keep the already computed homomorphism in memory in order to be able to reuse them and then to avoid to do several computation, useless computation. Okay, so how to encode this transition T of a given state? So this is done here by applying small homomorphisms. The small homomorphisms are, for instance, the homomorphism like that remove token. So minus is, for instance, for T1, this is the minus of P1, and there is, okay, maybe here there is something wrong because there is no, okay, it's 2. So you are removing twice P1, and then we have to decide if P1 is greater than 0. Otherwise, you cannot apply the T. This is the principle here. If the transition is not fiable, it means that there is no resulting marking, and so on. So I don't want to detail this aspect, but this is done by many homomorphisms that are building the behavior of the transition. So, in summary, we have made a way of computing M. Okay, so now this is a MFDD. So there is a representation in this domain, and we have to apply this representation to prove some property. So in order to do that, I have to define a logic. So I don't want to detail the logic. There is atomic proposition, logical connectors, and some temporal operators. So using this, we will able to produce algorithms for checking the satisfaction of a formula. So this is the algorithm for checking the next file. Okay, if I presented this, it's just because it's interesting to understand that now we have another problem. The other problem is the fact that we need always to use one operator, which is called pre. Pre is the fact that we need to understand from which state we are coming in order to check that the next state is satisfied. So there is a state that are satisfied, and now we need to compute the pre of this state because it's a way of building the fixed point of the computations. Okay, so now the problem is that pre needs to understand the relation between the state S1 and S2. So here there is 2 options. We can encode this notion into the decision diagram, And this is what, for instance, new SMV is doing, but this is not very efficient. Another way would be for Petri nets to understand that if I have a Petri net, the pre is just the reverse of the arcs. So this is the pre-relation. This is the relation. So just reverting the arcs allow you to know what is pre. So with this pre, you can check CTL formula, but because, for instance, for more complex formula, here there is a fixed point, but always we are using the pre. So if you know the pre, we are able to implement the model checking of CTL formula. Okay, so for Petri net, it's possible by inverting the relation, but this is possible for simple Petri nets. It's much more complex for high-level Petri nets, for instance. Okay, so in summary, what I explained is the fact that with decision diagram, we can encode sets. We have important properties such as the fact that the final representation is unique. We have a way of managing the operation on this decision diagram. So maybe it's not just SFDD, it's DD in general. And later we can encode the markings and the set of markings. So using algorithms that are global to the set of marking to produce, to compute more efficiently, for instance, the state space. We can encode the fire function in order to compute this state space. And finally, there is a problem of CTL formula that needs the pre-relation. And this is a problem because for high-level nets, for instance, it's not possible to compute it. We made some very complex inversion of the logic, of the semantics of the firing relation, but this is something relatively difficult, but probably possible. This is an open question for the computation of CTL formula on high-level nets. Okay, so in conclusion, I would say that what I presented showed that it's necessary in order to tackle the complexity of systems to modularize the systems. Even with some modularization, we have to manage the combinatorial explosion and to use, in order to manage this combinatorial explosion, adapted model checking techniques for encoding the states, for doing this idea of computing globally for instance, the state space computation. So instead of decomposing state by state and computing, to globally compute the evolution of the system, and finally to be able to check CTL formula. So that's it. Thank you. If you have any question, I would be happy to answer.
Okay, thank you very much, Didier, for this very interesting presentation. I'm sure there is questions from our PetriNet experts in this.
Yeah, maybe. Yeah.
There is one already on the Slack. Soumyadip,
Yeah.
you may want to ask your question directly, I think.
Oh, yes.
Yeah, I did it. Thanks for your talk. So I have just one question. Can you please go to the slide number 23?
23?
23. Yeah.
Okay.
Yeah. So if I take the right-hand side of the part, that is, why problem because
here.
yeah.
So the A, B, C, D. So this one means, as it is bottom, that it is not included.
It is not?
So it is not included in the family of sets.
Okay.
So, but if you look at the path here, A, B, C, C, D, and not D here, in fact. So ABC is included.
A, B, C. Can you please show in the screen?
Yeah. So I will take another color. So A, B, C, D. This is top.
Yeah.
Top. Okay, sorry, I didn't explain all details because it's a little bit long. Okay, so it means that it is a take, and this is a give.
Okay.
Skip. So when we have top, we take the node. When it is bottom, we skip the node. But don't. You need also to understand that the solid arrow is the take from the previous node, and the dash arrow is the skip.
Yeah. So that is basically the classical concept of the BDD. So the solid line for the.
This is very close to the BDD.
Yeah.
You can just, with BDD, you can just change the top and bottom by 0 and 1.
Yeah.
But what it changes is later what we can do with this structure. Okay?
Yeah.
Because there is, the canonical form is a little bit, probably it's similar, the canonical form. But the most important thing is about the homomorphism, the fact that you have operations that can be applied on the subsets. And there is this generalization, and later there is this generalization about map family decision diagram.
Okay. So I think Professor Sarkar have some questions. Because he's an expert on that, Professor Dipankar Sarkar. So
I don't understand.
No, actually, I think Shomadev has been asking me to ask questions regarding certain things. I am Dipankar Sarkar. Yeah. So essentially, if you could go further, you have been speaking about high-level patronates. So could you go to 41 or something? Somewhere you spoke about that high-level patronates. It's not yet. Yeah. So when you speak of this, that are you speaking of that diagram? I mean, the decision diagram representation of the patronate, high-level patronates?
Yes. Okay. So maybe I put some slide on this. Here, there is a paper here where we generalize the notion of decision diagram for representing terms. Okay. So with terms, we are able to encode high-level patronates.
So what I wanted to mean is in your high-level patronates, you do have data paths, right? I mean,
yeah, that's right. For instance, if I'm using this example, it means that in place I have some types. For instance, I can say that the type here is string. Okay. Here it could be I don't know, natural number. So the idea is with this high level that you have operation, for instance, taking a natural number and producing a string. For instance, X can produce a construct a string of, I can do something a little bit clever. here I will produce a string and put a condition saying that S is a string satisfying the fact that size of S equal to X. Okay?
No, there is another. Yeah, please proceed. I'm sorry.
So this is a condition for, okay, so sorry, I will just rewrite this. So it means that here it's a condition, and the transition can be fired only for instance of the variables here that satisfy this condition. Okay, so this is a very complex condition here, because it means that you are able to synthesize any string, for instance, A, B, C, D, that have the length X. For instance, I put 3 here, so or 5, no, 4.
4, yeah.
So this will produce a string like that, but all possible strings can be produced. So it means that the marking graph, starting with 4 in the place P2, will produce all possible strings with a length 4.
Okay. Yeah, true. I understand.
This is a very high-level model.
Now, in the accompanying CTL property specification, so you have such atoms, right, with equalities around these, like size equal to X implies. I mean,
yeah.
Okay.
So you need a CTL logic where you have something to be able to check the property of the local property of a place. That's right. Okay. You need, okay, probably I have here a definition. Okay, in the atomic proposition, here it means that size of S equal to S prime equal to S second, or many operators are defined on the place.
Yeah, true. Now, what I'm asking that, I mean, has it been covered in the state of the art? I mean, what is the state of the art regarding this kind of petrinets?
Yes, the is the definition, the ISO definition of the petrinet. This is high-level petrinets are defined in the ISO norm. So this is a norm for the high-level petrinet. So there is a definition of everything that I mentioned here can be defined using this ISO norm. I don't remember the number, but this is something that you can find easily.
No, I am speaking about that your this state space, I mean, representation using decision diagram of such petrinets, and then model checking on them. What's the state?
Yeah, okay. This aspect, there is an Alpina tool that has been developed in my group in Geneva. Unfortunately, I think it is not working anymore, but okay, it was a Java tool.
But it is available in tool repository. I think Internet World Tool Repository. Alpina is
okay.
You have found the Alpina somewhere.
Yeah, it's an Eclipse-based tool, if I remember well.
yeah.
Okay. And
So
yeah, another thing is that you have timed petrinets in the literature. So has there been anything about temporal CTL being tried, model checking, and using this kind of SFDD for timed patronage?
No, no, not at all. But I think the difficulty in general with time patronage is to have a finite representative of the behavior of the system, which is not so easy.
Okay. Okay. Thank you. That's
because here we are completely finite, because the problem of time is about the fact that it could be defined on relative on rational numbers which are dense, so it's difficult.
Okay, thank you. Yeah, that's all.
Thank you.
Okay, good. Thank you.
So maybe we should end here because we need to move on to the next talk. So thank you very much, Didier, for this talk. And
thank you.
Yes.
So just to say that I am happy to answer other questions if offline some want to ask.
Yeah, maybe we should do a project to fix your tool.
Yeah.
Okay. Okay, thank you.
Thank you so much.
Thank you. So our next speaker is Professor Santonu Sarkar, who is actually adjunct professor at BITS, Pilani. And Santonu received his PhD degree in computer science from IIT Kharagpur. And he has more than 20 years of experience in the IT industry, so he did a lot of research for industry, and has also a very good experience in the academic world. So he's kind of a good hybrid person. And he is also he has been granted a total of 15 patents and several publications in many journals and conferences. And his current research interests includes the building software engineering techniques to ensure dependability, performance, and ease of use of clouds and HPC applications. Welcome, Santonu. Are you there?
Hello, can you hear me?
Yeah, we can hear you. And so your talk is going to be, can you show your presentation? So cyber physical systems design, cyber physical system driven digital twins for industry 4.0.
Just wanted to check if you can see my screen.
Yeah. Okay, that's perfect. We see it very good.
Very good.
Yeah.
Okay.
Okay, so I let you go. Thank you.
All right. Thank you very much. In this talk, what I will do is I will give a brief overview of digital twin for industry 4.0 and what are the modeling techniques that are being used. So as Dominique said, I'm an adjunct faculty of BITS Pilani, but also I am right now a senior principal scientist in ABB Corporate Research. So ABB Corporate Research is focusing on various interesting industrial automation related areas. And so digital twin is certainly one of the area of interest. And what I'm going to talk about is more of a overview and industry kind of overview of this digital twin. So I changed the slide. Just let me know if you can see the slide number 2. If you can, just let me know. Okay. All right.
Yes.
Good. Okay. So digital twins are is kind of I mean this term was first introduced sometime in 2002, and it basically said that it is a virtual representation of a production system, and very importantly, it ensures that there is a synchronization between the actual system and the virtual system. And this synchronization happens through the sensor data. Now, after that, of course, this term has become quite popular. And in fact, most of these smart industries or Industry 4.0, this kind of terms that we see here with, in many industrial systems or industrial plants, digital twin has become quite popular, and people are actually looking at different aspects of digital twin. They're trying to see how digital twin can be leveraged to improve the production process. So, various things so can be actually modeled using digital twin. As I said earlier, it is basically a digital replica of a physical system. So therefore, any physical systems can be modeled, or one can attempt to model any physical system at any level of granularity. For example, one can just have a discrete component like a gearbox or a motor or a valve or a pump. Or it could be a composition that you have a set of discrete components and then you combine them together to form a more complex equipment. For example, you could have a gas pipeline, digital twin, using individual digital twins. There could be another model which is a peer-to-peer, where there are a set of similar digital twins interacting with each other. For example, a modeling of windmills. Each windmill could be a digital twin, and wind farm can be a digital twin comprising of a set of windmills interacting with each other. So Dominic, just wanted to check with you that I guess my talk ends at 7:30, I guess, right? Is that right?
Yeah, in any case, I think we're over time. So if you can try to, you were supposed to have 1 hour, right?
Right, but I think I'll be able to finish it by 7:30.
Okay, that would be perfect, actually.
Yeah. Okay. So so the kind of things that one can answer here, for example, if you want to really model a motor, and then the question could be that at what temperature you should operate a motor so that it is not overheated at the same time, it runs for a long time. And that question you're answering, even before the motor is running, again, based on the model. There are various examples. For example, in the case of oil and gas, you are actually monitoring an oil well using a digital twin, and you're using simulations to actually you actually use a well-known simulation models for seismic data. But the point is, of course, the seismic data or any other subsurface data-based model simulations has been there for a long time. It's not that this is new. But what is new today is that you are actually combining these models with other digital techniques, and basically try to answer more complex queries. That's what is more important here. In a chemical process, for example, there could be sensors. Now, in this case, this digital twin of a chemical process runs along with the actual physical chemical process, where the digital twin is getting the data from sensors, which is providing temperature, pressure, etc. And it is, as the chemical process is running, the digital twin is also performing simulations from this real data to predict the optimal production parameters. And then that simulation results are then shown to the operator, or sometimes maybe it is directly controlling the process to fine-tune the parameters. So that way, this digital twin and actual physical element are coexisting rather. And I mean, people have been showing a lot of interest, as I said earlier, and some of these industrial reports basically suggest that from basic engineering of any plant or design, from the design to actual commissioning, that time can be significantly cut if the digital twin based analysis is used, because a lot of testing, verification, what if analysis can be done using this, and then the time can be really reduced. So again, as I said, that now it has become quite popular, and then specifically in Europe, Germany, it is quite popular, and big industrial houses, ABB is certainly one of them, Siemens, and many other companies are actually looking into these techniques. Of course, GE is also working on this. Now, there are various ways to actually model a digital twin, and in fact, there is no single way to model, and people have been trying all different techniques. So one model that I call to be a semantic driven model, which is supposed to be a high fidelity model. So for instance, one can use multiphysics, multi-scale kind of a probabilistic model. These are quite precise, continuous time domain model, but it is restricted because you don't really have a very precise physics or very nice algebraic formula for each and everything, you know. So therefore, in some cases, of course, you can use, but in some cases it may not be available. Then you can you can get into the next level of model, which is more of a medium fidelity or low fidelity model, which is more of hybrid automaton or a discrete event system kind of approach that has a broader applicability compared to the high fidelity. The second one is a data-driven model, which is also getting quite popularity because of the artificial intelligence and machine learning becoming quite popular and becoming quite a handy tool in every domain. It's true for industrial systems as well. So here, this AI ML models really do not capture any physical dynamics like physics or like any automaton, but it basically collects the operational data from the plant and tries to correlate certain parameters of interest from the input data points. And one of the issue here is that, of course, it is quite versatile, but at the same time, you really don't have the model of the plant and actual plant and the model. So that traceability is not there because you're just simply getting the data and creating a black box model. Of course, people are trying to build traceable AI or traceable ML models today, but it is not as good as, for example, a multiphysics based model. Therefore, for example, if you want to find out anomaly or certain failures, that is possible. But if you want to really trace back and find out why it happened, a root cause analysis, that may not always be possible. Third one is a visualization model where it is building a kind of a 3D or even augmented reality model, which is basically a model that more or less depicts the actual physical thing, which helps the operators to do to get familiar with the actual system. Now, so with the physical system and with the digital twin, there are various levels of integration. The first one is manual, where there is where you have basically the digital model and the physical object, and the data from a digital model going to physical object, or the data coming from physical object, which is feeding to digital model. They are all manual. So that's why it's called a digital model. The second one is called the digital shadow, where what happens here is that the physical object, from the physical object, you get the data in real time, and the digital shadow basically fine tunes or takes a decision based on this data. But from digital shadow going to physical object, that is manual. Whereas the third one, which is more of where everything is automatic, and then they basically, the digital twin replicates the physical object, that data flow, that's completely automatic. Now, while that's technically speaking, this is a digital twin, but you will find that in industry today, people are actually using all kinds of approaches, like more offline model, like digital model or a shadow, In fact, digital twin, in its strictest sense, is still not being used today. So if we look at the modeling approach, I'll just take a simple example of, I mean, I could have taken some examples from the industry, but again, that might have some kind of a confidentiality issues, which is why I'm sticking to a very standard, familiar example of a cruise controller. If you are to, let's say, build a digital twin of it, then one could be the component. For example, you want to model the car itself, and and you want to, with respect to cruise, of course, when you are modeling a car, you can model so many things. You can even model its interior and so on, but you are not interested in that. You are interested in only that part of the car which affects the cruise controller. Therefore, you only build a model of the car, which basically models the change of the speed with respect to the force, which is basically based on Newtonian physics. And you are actually computing the velocities given the force and given the like frictional force coefficient. Now, so essentially, if you are computing what should be the acceleration and so on, that you can actually use using this kind of physics based laws. Here again, you are taking some assumptions. Specifically, you are assuming that, let's say, the friction is proportional to speed. You are assuming that the rotational inertia is actually quite negligible, and with that assumption, you are actually building a model here. Now, well, that's about the car. But for example, if you want to really build another feature of the cruise controller, which is how do we basically have a scenario where the cruise controller automatically attains the desired speed when it goes into autopilot mode, then you can basically have this. Of course, you can have this component car model, but you can also have something like a temporal model where you can have this kind of clauses like eventually this system is going to reach the preset cruising speed in an autopilot mode. And the moment you have this kind of a formula of eventually reaching a certain state, then that you can build it using a transition system, and there you can perform various safety and liveliness properties. Then there could be a hybrid model, which, for example, you want to build a PID controller where you are getting the current speed and that current speed you might be getting it from the real sensor, and the driver sets the desired speed, and the output is that what should be the desired force F that will be eventually achieve the desired speed. Now, that in order to do this, you need to have obviously the physics-based model, plus you need to do simulation. Slowly things become more complicated. Suppose you want to do more of a manual control. Assume that you have got a cruise control, and then you have got some plus and minus button, and then you are increasing and decreasing the speed from the user. Then how do you model that? Of course, assuming that you are getting the speed of the car from the sensor, and you are sampling the speed at every clock. The moment you start sampling at each clock, maybe 1 second, 2 seconds, whatever it is, it becomes more of a discrete model. And so you can have all kinds of model. You can actually combine all of them, or you can have one or two types, depending on what you need. And they are all, in my opinion, basically becomes various types of a digital twin. There are various modeling languages that one can use, and people are actually exploring quite a few. For example, one could be AADL models, or architecture analysis and description language, which is a DSL to describe cyber physical systems. There could be automation ML language, which is also another DSL to describe components or modules in a process industry. So in AADL, there are very interesting features. For example, AADL language allows concepts like flow units. One can actually model flow units. One can model the processing elements. One can model things like actuators, sensors, devices, using the clause called device in AADL. There could be a notion of physical channel, which could be modeled by a bus of AADL. there could be software composition. So actually, ADL has quite a rich modeling features using which you can build a reasonably complex digital twin. Now, basic ADL actually has the discrete behavioral model, but people have also added different annexes are essentially plugins which extends the ADL functionality. I'm quite sure that in this audience there are quite a few people who understands ADL much more than me. But nonetheless, for the sake of completion, I'm just saying this. So hybrid annex essentially tries to add this continuous dynamic system, like kind of physics-based stuff with ADL, and it's a quite a vibrant community. Automation ML again, that basically is a language which basically allows you to define a complex module comprising of different components and using something like instance hierarchies with interfaces and their connections. And it's the one good part is that inside the automation ML itself, each instance has one can do a type verification, because the type definition is also there as a part of the automation ML document, using system unit classes, role classes, interface classes, using which you can do a type checks. One example could be, I've just taken it from a paper, a digital twin, let's say, of a valve, which one can describe using AML, and that can basically one can do a simulation of this valve, and one can check the different parameters of the valve using another application which can interact with the digital twin. This picture I have taken from a paper which I have marked it here, which is basically the digital twin data model with automation ML and like communication modeling, this particular paper. So here this valve is modeled using automation ML, and then one can interact remotely with this. Now, automation ML also has a state model, which basically represents its behavior, where again, this is a standard IEC 61512 standard based state model, where it says that at what state this module can be, and most important part would be the running state, in which one can actually put things like, let's say, kind of a more complicated control logic that is executed when it is running. So of course, ABB and other companies are actually working on this automation ML based designs, and then simulation and also code generation from here. The data-driven model, as I said, that's completely it uses AI and ML that can run on cloud or on edge devices. One example could be a smart energy, for example, where you build a digital twin of a solar power system which is running on an edge computer, and then it collects the data from actual solar plants, power grid, as well as what is the current weather condition, and then based on that it can actually predict various operational and control parameters which can actually balance the power grid stability at the same time, and based on that it can basically activate or deactivate the solar plant, and that can run on an edge device to take a real-time decision. There could be another example of condition monitoring of a physical device. For example, it collects the real-time data of a physical system that is running, and it can predict whether this is going to fail based on certain anomalous conditions. For example, in a manufacturing plant, one can get real sensors data, as well as there could be a physics-based soft sensor which can also give data. And this digital model can be a hybrid model which can get data from both real sensor as well as the soft sensors simulated data, and it can predict, for example, optimal flow rate, temperature, and so on, and that can be suggested to the operator, which is actually controlling the actual controller. In the case of visualization and augmented reality, so a support person can look at an object through camera or interact with an image of an object with more of annotated labels or overlaid information on a particular image, and then do certain operations and understand the intricacies. Sometimes it is mostly used for training today, but it could be used eventually. This can be also integrated with other types of digital twin for more complex operations. So one could basically get a continuous flow of data to represent what is happening in the real physical object, and based on that, one could basically even build a physical model. But today, these visualization models are mostly used for training and more of an understanding purpose. Simulations are very important aspects of digital twin, which basically tries to, using simulation, one can basically understand various properties of a physical system. So for example, let's take an example of a digital twin version of electrothermal analysis of actual voltage switchgear, where this is a power grid equipment, and it need to be compact and efficient, and it should be able to handle, let's say, extreme thermal stress. So digital design techniques could be used for this purpose, for electrothermal simulation, to understand the characteristics of this particular switchgear, and that can actually reveal a lot of interesting part. So one can integrate actually a CAD design of this switchgear, and it combines with simulation, for example, using CFD solvers or any other finite element method to understand its functionality. Another example, again, I have taken it from this time series behavior modeling with digital twin, this paper. This basically simulates electric vehicles that are running in a city, and it tries to understand the electric vehicle movement, and it considers things like how much energy this electric vehicle is consuming. It simulates the traffic movement, and it requires obviously the physics-based motion synthesis. But very importantly, it also puts, let's say, charging stations at different points, and then tries to find out whether there are optimally placed charging stations, so that these electric vehicles, when it runs out of energy, it can go to the charging station. So that could be, so this kind of analysis can be done using this electric vehicle movement simulation. So digital twin is a very important component of Industry 4.0. So Industry 4.0 is basically a jargon term. Again, I mean, that's mostly popular in Germany and many other European countries. Of course, it is used with different names in the US, but idea is the same. It is basically, it focuses on creating the intelligent products or processes using IoT devices, services, data. And when I say Internet of Data, it basically means it is collecting data from all different sources. And IoT and Industry 4.0 is actually gaining momentum in areas like smart power grid, smart energy, smart logistics, smart building, plants, and so on. Here, a small picture of this could be like this, that here, the smart factory, from the so-called smart factory, there are smart devices which are able to communicate with each other through like IP physics, for example, and they send data which is going to be stored in a really large cloud-based data center, edge and cloud-based data center, which is often called data lake, and on which this data is coming. And then from this data, people can do multimodal visualization, have analytics which can do various types of optimization of the overall products or even the process, so that the smart factory is actually optimized. Roughly, that's one way to look at it, of how Industry 4.0 would look like. Now, the digital twin in the context of Industry 4.0, as I said, that it is basically a key driver. I mean, our digital twin plays a very important role in realizing the vision of Industry 4.0. Most, as of today, in fact, this prognostic and health management is one of the key aspects of IE 4.0, health management of the devices or components or even the plant. So in that area, digital twin is used mostly today. For example, using finite element model, one can do some structural analysis. One could do monitoring. For example, one can check the operational state of an aircraft wing using, for example, Bayesian models. Failure analysis, a digital twin can actually simulate a tire touchdown, wear and tear, and probability of failure, maybe combining physics models, a multi-physics model for fault diagnosis of a fleet management system. What is the optimal parameter so that the factory can run with most efficiency? For example, it can predict the accurate cooling rate that need to be set. What is the melting rate that have to be set for a manufacturing process? So, and that can be given to the operator, and the operator can actually fine tune it. Or in the best case, it can actually control the plant itself. That's the basic goal of Industry 4.0, which is completely automated and as less human interaction as possible. So that's at a very high level. I wanted to give some of the areas where a digital twin is being used in the industry. As a closing remark, essentially, organizations have been offering digital twin without knowing fully as a part of IoT solutions. But nowadays, they are actually explicitly saying that they are offering digital twins as a solution. Like, for example, companies would be saying that, well, I can offer a digital twin version of a particular motor to a client, and the client can basically do analysis on that motor, and then test few things before even buying that particular motor from the company. So this digital twin can be offered as a service. Then a digital twin and the physical counterpart, as I said earlier, they actually interact with each other. In an ideal scenario, they should interact with each other in an automated fashion and interact. Large amount of operational data that need to be modeled, and therefore data-driven models are also quite popular. Multiple types of modeling: semantic model, data-driven model, visual models. Simulation plays a very important role to understand various intricacies of the system. And quality of service, again, is a very important part. Most importantly, people are looking at quality of service, like, for example, safety analysis, fault tolerance, security and interoperability of this digital twins. Assuming that, let's say, digital twins are coming from different companies who are selling physical assets. If that comes, and then if I want to take the digital twin from somebody else, and then I want to use it in my system and do analysis, that's basically becomes an interoperability issue. Security is certainly a concern because these are all cyber physical systems. Therefore, it requires, of course, they are all internet enabled. So question is that how do you do it without breaching the security? So that's basically a high-level talk that I prepared for this workshop, and that's all from my side. I'll be happy to take questions if you have.
Thank you very much for this very interesting presentation and on these digital twins. I will first check if there is some questions on Slack. No questions on Slack. You know, also I find it interesting that how this term digital twins showed up at some point in time, because people have been doing modeling a lot for much longer time. And I guess the main characteristic of digital twins is that they follow the actual real system. They are updated according to the change of the state of the real system for the properties you're interested in, right?
Yeah, that's right. So earlier it was more of offline. Now they're trying to make it more of a real-time interactive.
And there is actually there is a community in the model-driven engineering, like for example the models conference. There has been always a workshop called Models at Runtime, which is I guess is a bit similar, but probably used more for software systems or things like that. Where the models is basically also playing the role of the digital twin. Someone else has questions?
May I ask just one question, Santonu?
Yeah, hello.
Yeah, hello. I could not understand that interaction between digital twin and physical object. Physical object, see, basically, is there another set of models? I mean, another model for physical object? If you could throw some light on that?
Okay.
You had that diagram where there are three. I mean, you spoke about shadows. So that diagram possibly will help. That slide.
Yeah, sure. I'll come to that slide.
Yeah, sure.
Okay.
Sure.
So what I meant is that these physical objects can be anything. It could be, let's say, a valve, a motor. It could be even a plant having all those. So assumption here is that these physical objects are kind of smart, as in they kind of expose their internal states through some means to the external world. And nowadays, these smart devices are coming up, like smart motors, smart valves, smart MRI machines, which are essentially exposing its own internal states, at least some part of the internal states, through events. And there are now standards which so in other words, these physical objects are connected via LAN. Okay, and they publish the events periodically as it runs, which basically shows its internal state. So that data, when it is connected to LAN or maybe through wireless, network, assuming that there are 5G kind of connectivity in the plant, so that data is streamed, and that data is collected to the digital twin. So the digital twin has its own version of or a digital avatar of the motor. Okay, and that avatar of the motor, for example, is getting the data from the real motor, and it is getting those events. And in the digital twin, what's happening is you have built a few analysis techniques, which could be, for example, by looking at the data, you could have analysis. For example, is it really running at extreme speed, or runs at this speed, or if the internal temperature of the motor is this, will it run for long? And this kind of analysis, and it can guide the operator to accordingly fine tune it.
So is this kind of interaction also used for validating the model?
Yes, validation means that you typically check for example, if you are building more of a discrete model. Okay, say I was talking about the cruise controller, where you have a scenario that the digital twin can analyze, even though you are saying that eventually this particular cruise controller will the speed that is defined by the operator. Question is that can actually do let's say safety analysis or even reachability analysis. That it will reach, but when? And for that, the data that might be needed, obviously the events that are there using which you did the model, that events may come from the real system.
Okay, thank you.
We have another question from Hans on the Slack. So Hans says, often multiple identical, at least initially, machines are deployed. Would there be a unique digital twin per machine, or would there be a digital twin aggregate information, sensor data from all deployed machines?
Okay, so this is an interesting question. Actually, this basically leads to another topic which I have not touched at all here, which is more of an information model of digital twin, where there is a type. So there is a concept called type, and there is a concept called instance. So you have, for example, a motor type, okay, and you have a digital twin for that, and you have got instances. You may have 3 motors of the same type. So then you have 3 instances of the digital twin running, and then you are going to get the data from all the 3, which all comply to the same type.
Okay. I don't know if that answers your question.
I mean, is that what you wanted to know, or?
I think that's what you want to do. So there will be so there will not be 3 instance models, 3 digital twins of the 3 motors. They would just done one.
Do you really run 3 physical instances, or you basically have the same type but just collect the data from all the 3 physical instances and then label them as if they are coming from three different instances? That depends on how you want to model it efficiently. But ideally, you should, I mean, a naive way of doing it is certainly have 3 instances in your digital side where you are doing the analysis. You can actually have 3 instances running. In fact, it would be a better idea to have 3 instances running because they're all active objects. You are having active objects, so it may not be a good idea to combine all the 3 into one.
But what you're saying is that in some cases it may be implemented differently as an aggregate or something, right?
Depending on what you want to model. If you want to really model the entire plant having, let's say, 10 motors, 60 valves, and you want to monitor each and every valve's condition, even though the valves are all similar, even though the motors are similar, even though the PID controllers are similar, you may require those instances because you may want to really check the health of each of them. The same algorithm might be running, say the algorithm to, let's say, detect anomalies in a motor. That is the same, but one motor might have a different parameter compared to others. So those 3 algorithms would run in parallel and they would get different data.
Okay, yeah, thank you. Very good, very interesting. And so do we have any other questions? I don't see anything on Slack. Okay, so thank you very much for your presentation. And I guess we can take a short break till 4:30 in Europe and in India. That corresponds to 8 o'clock for the panel discussion, which topic will be challenge of CPS development, AI ethics applications. And we will have Hans Vangeluwe as a panelist, Samit Chattopadhyay, Santonu here, who just gave us a presentation, and Vinay Kulkarni and Rina Shirvalat. So we'll come soon to this interesting panel discussion. Thank you.